A. Speed, frequency, and wavelength are various parameters connected with wave. What are the parameters which remains the same on 1. Reflection and 2. Refraction? So let us discuss question A, okay? So we want to understand reflection of wave, okay? Let us consider a plane reflecting surface. So this is a reflecting surface, and this is normal to surface, okay? So this is incident wave making angle of incidence I with the normal. So this is incident wave, okay? And let the incident wave be in air medium, okay? So I'm taking air medium, okay? So we have this. And after reflection, we have reflected wave making angle of reflection R with the normal. So this is a reflected wave, okay? So what we find, reflected wave is in air medium. So we find this, and let V be the speed of incident wave in air medium. So we find reflected wave, okay, moves with same speed. So this is speed of reflected wave, and this is speed of incident wave, okay? So we have this. Clear? We find this. Clear? So I'm writing in reflection, okay? In reflection, incident and reflected, incident and reflected waves are in same medium. So this is to be noted, okay? So we have this. Therefore, we find, okay, in reflection, we find speed of incident and reflected wave is same. So we can write in this way, speed is same. Okay, so we find this, speed is same, and frequency. So frequency of incident equals to frequency of reflected wave. So we find this, okay? So frequency is same, and wavelength of incident and reflected wave is same, okay? So we find wavelength of incident equals to wavelength of reflected wave, okay? So let me write in this way, okay? So we find wavelength is same. So we have this. Now let us discuss refraction, okay? refraction. Now, let us consider this case, okay? We have rarer medium, okay, having refractive index mu1, and we have denser, okay, medium having refractive index mu2. So what we find, mu2 is greater than, so I'm writing over here, we find this, okay, mu2 is greater than mu1. So we have this refractive index of denser medium is greater than refractive index of rarer medium. So this is normal to the surface, okay, and we have incident wave making angle of incidence I with normal. So this is normal and this is incident wave, okay. So we have this, and we know after refraction the refracted wave bent towards normal, okay. So this is a refracted wave bending towards normal. So we have this. Clear? Now, since we have two medium, okay, so the speed of incident wave, let's say v1 is the speed of incident, okay, and v2, this is speed of refracted wave, okay. So I'm writing in this way. Since we have two medium, so the speed is not same. So this is to be noted, okay. So what we find in case of refraction is that, okay, we find in refraction incident and refracted waves are in different medium. So we have this. Now, from this figure, okay, from this figure, what we find is that, okay, speed is not same. So we have this. So V1 is not equal to V2. So we have this. Clear? So what we have or what we find is that speed in rarer medium is greater than speed in denser medium. So we find this, okay. So we need to note this. Next, frequency, okay. Frequency is same. So frequency of incident and frequency of refracted wave is same, okay. So we find this frequency is same. So we find this. And what about wavelength? Wavelength is different, okay. Wavelength is different. So I'm writing this is wavelength, okay, and wavelength is not same. So we have this. Clear? So lambda 2, this is wavelength of refracted wave. So wavelength is different. Now, from this figure, okay, let me write over here. Now, if we have this, so we can look or we can see from this figure, okay, refractive index of denser is greater than refractive index of rarer medium. So if we have this, okay, then we find speed in denser medium is less than speed in rarer medium. Okay, so we have this. So we have this. Therefore, the wavelength in denser medium is less than the wavelength in rarer medium. So we have this. Okay, and this is to be noted. So if we have this, then it means that wave get squeezed. Okay, so it get squeezed. So we have this. So when we find wave traveling from rarer to denser medium, clear, then speed is not same, frequency is same, and wavelength is different. And we find wavelength in denser medium is less than wavelength in rarer medium. It indicates that the wave get squeezed. Now, if we have this condition, okay, let's say if we have this condition or situation, so this is the boundary separating two medium, okay. Let's say we have a denser medium having refractive index mu1, and this is normal, and we have incident, okay, wave traveling in denser medium. Okay, so we have this. So this is incident wave, and we know after refraction the refracted wave, so this is refracted wave, this bend, so this bend away from normal, so we can write in this way, bending away from normal. So we have this, and this is angle of refraction. So we have this, okay, and let v1 be the speed. Okay, so this is the speed, so this is the speed of incident wave, and let v2 be the speed of refracted wave. So we find speed is different. Okay, so we have this. Now let the refractive index of this medium, okay, so this is the rarer medium, this is the rarer medium having refractive index mu2. So we have this. Clear? We have incident wave in denser and refracted wave in rarer medium. So what we find in this case is that, okay, if mu2 is less than mu1, so we have this. Clear? Then what we find is that speed in rarer medium, that is v2, is greater than V1. So we have this. Therefore, we find lambda 2, okay? Wavelength of refracted wave. And what is lambda 1? This is wavelength of incident wave in denser medium, okay? So we have this. Lambda 2 is wavelength of refracted wave. So we have this. So what do you find? Lambda 2 is greater than lambda 1. So we find this. So we find this. Okay? So if we have this, then we find wavelength of refracted wave in rarer medium is greater than wavelength of incident wave in denser medium. So in this case, wave get stretched, okay? So we find this. So we can draw conclusion that, okay, in refraction, speed, so we find speed is not same, okay? That is speed changes, okay? And we find frequency, okay, is same. Frequency is same. Next, wavelength, okay, is not same. So I'm writing in this way. Wavelength is not same. That is, wavelength is different for different medium. So we have this. Clear? Now, let us go for question B, okay? What are the assumptions on which Huygens principle is based? Does it apply to sound wave in air? Assumptions of Huygens principle, okay? Now, before discussing the assumptions of Huygens principle, let us understand, okay, and brief about wavefront and wavelets, okay? So wavefront is a surface, okay, it is a surface of constant phase. Each point, so we need to understand this, okay? Each point on a wavefront acts as a fresh source, okay? Act as a fresh or new source of disturbance, okay? So we have this called secondary wavelets or secondary waves. So we have this. Clear? Now, assumption 1, okay? Each point on the wavefront acts as a fresh source, okay, of new disturbance called secondary waves or secondary wavelets. So we need to understand this, okay? And the wavelets originated, okay? Originated from these points spread out in all directions with the speed of light. Assumptions 2. The envelope or tangential to the surface, okay? So let me write in this way. Tangential to surface of the wavelets in the forward, okay? And the forward direction gives, okay? Gives the shape and position of the new, okay? New wavefront. New wavefronts after any time t. So we have this. And next, we have, does Huygens principle apply to sound wave in air? So let's understand this. We have this, okay? Does Huygens principle apply to sound wave in air? So we have this. Next, we need to understand this, okay? We know sound wave, okay? A sound wave are longitudinal, okay? Are longitudinal waves. So we have this. Now, according to Huygens, okay, light travels in the form of longitudinal waves. So I'm writing, according to Huygens, light travels in the form of longitudinal waves. So Huygens assumed that light travels in the form of longitudinal wave. So we know sound wave is longitudinal wave. So Huygens principle can be applied to sound wave in air. Principle can be applied. Let me write in this way, okay? Sound wave in air. So we have this. Now, solution for C, okay? Question C. So let us see this, okay? Question C. Figure represent a plane wavefront AB striking a surface in air, okay? The refractive index of the glass is 1.5 and the speed of light in air is, so this is missing, okay? So we know speed of light in air is 3 times 10 power 8, okay? So we have this. The distance BC is 3 centimeter. Find the length AD if CD is the refracted wavefront. Comment your answer. So we have this, okay? Now, in order to solve question C, okay, we need to understand this. So I'm redrawing this, okay, figure once again. So we have air and glass, okay, this is XY boundary separating air and glass. So we have this. So this is A, this is D, this is B, this is C, and this distance is 3 centimeter. Okay, we have this. Clear? We have this. So what we have is that refractive index of glass, okay? Refractive index of glass is 1.5. This is given, okay? So we have this. And speed of light in air, okay? Speed of light, C is 3 times 10 power 8 meter per second. So we have this. Distance BC, okay? BC equals 3 centimeter. It is given, okay? So we have this. And we need to find length AD. AD is what? Okay. If CD is the refracted wavefront. So CD is what? Refracted wavefront. So let me write over here. CD is refracted wavefront. So we have this. Now, in order to solve this, okay, we use this concept. So we know from the theory, okay, what we know is that, okay, in the time, disturbance from B, okay, reach to C. Disturbance from B reach to C. The secondary waves from A, okay, it travels a distance AD. So we have this. And what we get is that, okay, BC, this equals C times T, okay. So we have this. And AD, distance AD equals, let's say the speed in glass is V, okay. So this is speed in glass medium, okay. So we have this. So this is V times T. So we have this. Clear? We have this. Now, let us find this, okay. BC by AD. So this equals C times T divided by V times T. So we have this. So we get BC by AD equals C by V. So we have this. Clear? We have this. Now, let us do some rough work, okay. We know absolute refractive index, okay. So I'm writing in this way. Mu equals C by V. So for glass, we can write in this way, okay. Since we have a glass, so refractive index of glass equals ratio of C to V. So we have this. Clear? We have this. Now, what we get from this equation is that, or from this expression is that V equals C by mu G, okay. So we have this. Okay, we have this. So we are going to use this equation or relation in this equation, okay. So we have BC by AD equals C divided by V. So this is speed in glass, okay. So this is speed in glass. So we have C by refractive index of glass, okay. So we have this. Clear? So we can write in this way, BC by AD equals C times refractive index of glass divided by C, that is speed of, we have this, okay, speed of light in air. So this cancels out and we are asked to find AD, okay. Therefore, AD equals BC by refractive index of glass, and BC is 3, okay. It is 3 centimeter and refractive index of glass is 1.5. Therefore, distance AD equals 2 centimeter. So we have this. Clear? So we are getting this. So we are asked to comment, okay? Comment on the result. So what do we find? AD is less than BC. So we find this, okay? AD is less than BC.